Hello students, how are you doing today? Okay, so this is Dr. Archana Dongre and today we are going to study this topic. We are going to revise this topic, deflection of beams using energy methods. Okay, so an interesting topic. So how this topic, what is the need of it? Why are we studying it? Okay, so if on a body, when we consider any structure, okay, you consider any structure, any beam where some load is acting. Okay, so let's consider a load on that. Different type of load, mag, it may be a point load or it may be a UDL, W per unit length, say kilonewton per meter, say it is in kilonewton. Okay, so because of this loading, there, because of some external loading, this is external loading, some deformation happens. Okay, there is some deformation happens in the structure, in the B. Okay, so some load is there and then it's getting deformed because of some external loading, it is getting deformed, so we call it as work is done over there. Okay, so work is done, so that is one stage. Okay, so what I said, when any beam is there, when some load is acting on it and it goes under some deformation. Okay, it goes under some deformation and then we call it as work is done. Okay, so this is a process. So this is because of the external loading what is happening. And there is also one thing, one thing happens in that, when the deformation, how does that deformation happen? Okay, so there is one important effect. So there is a straining effect. So straining effect in the material of the structure. Now if you so this is this is regarding external loading. Now what is happening with the internal? Okay, so whenever some external load is acting on a structure, then definitely there has to be some internal resistance. Okay, some internal resistance should be there to resist that load. Like, when so much of in day to day life you have so much of tension. Okay, now exams are approaching, maybe for you it might have started also. So when exams are approaching for you, so much of pressure is there. Okay, so then with that stress, your body is actually, having some internal resistance to that stress. And then we go for meditation or some yoga or some exercise. So we do that internal engineering. Okay, internal work we are doing, so that this external load of this study and exams, we can take that stress really with all good strength. So similarly with these materials, with civil engineering structures also, whenever some external load is happening, there is some internal resistance. Okay, internal resistance provided by the material. Okay, and that internal resistance is, it starts from the zero. So when whole load is there, so it starts from zero to the complete load it can take. Okay, so to the complete potential of that particular material. So it takes that load to the full potential. Yeah, there is one, just an example. Full capacity will be a better word. Now if you consider an example of a person who is a weightlifter. Okay, so a person is there. Now you have seen it in many times, in competition, in movies, this is always there. Now just think, so much of weight he has, he or she pulled, she hold so much of weight on his hands, or the whole load is getting transferred. So how that load, what is the capacity, it can so it may be a 50 kg or 100 kg. There is so much of lifting competition we see. Okay, so here they can hold this much of load. Okay, so and they, you see them that they are the and finally they, the total load, they take it, and we don't see any tension in their face. They are in a smiling face. So they have their internal capacity, they have their internal resistance to carry that much load. Okay, so that is their capacity. So there is some, when there is some external loading, okay, on a structure, there is something internal resistance happening from the structure side as well. Okay, so here, okay, so hi Karan, I see a Karan joined over here. And so so this internal work which is stored as energy, okay, so this internal work, it is stored as energy, and it is due to the straining of the material, as I said. Okay, it is because of the straining of the material, so it is called as strain energy. Strain energy. Okay, so what it is? It is about the internal work. Okay, so internal work. So this is a internal work. Internal work due to energy stored. So internal work due to energy stored due to straining effect. Due to straining effect is called as strain energy. Okay, now when this perfect equilibrium is reached, okay, so for this conservation, so there is, as per the law of conservation of energy, this work done by the external forces must be equal to the energy stored. Okay, so the whatever work is done here, this work, whatever work is done, it must be, okay, this work done must be equal to this strain energy, because of the internal resistance, whatever it's given by the body. So this two should be equal. So with this, the concept of energy balance is used. Okay, so there is a energy balance. There is a energy balance. Okay, so this energy balance, we actually use it for the structural analysis. So this structural analysis one, wherever you are studying this deflection of beam, so this actually energy balance concept is used. So there are three methods to find out the deflection of beams, okay, using energy method. So whenever you hear that energy method, does not mean that it's only strain energy method. Okay, so there are basically three methods. So the three methods. So first method is strain energy, or even it is called as real work method. It is strain energy. It is also known as real work method. Then there is virtual work or unit load method. Virtual work or unit load method. And then there is third method, which is Castigliano's method. So theory behind these three methods, you can visit Ekeeda classes are there. Okay, so you can find my videos over there to get the theory part. Okay, now this particular class is for the revision. Okay, so we are going to solve a few questions based using whatever as per our time limit, we are going to use one or two methods, and we are going to find out what is the deflection of beams using energy method. Okay, so here let's see the strain energy method. Okay, so with this, let's consider one beam. Okay, a simple example we will start with. Let's consider a cantilever beam. So here our question says, okay, so using strain energy method, we have to determine the deflection of the free end of a cantilever. So the question says, this is a cantilever. This is cantilever, and it is having a load P kilonewton acting at the free end. P kilonewton, it is acting at the free end. Okay, and the span of the length is in L. Okay, we are not writing currently this is units over here. Okay, so units can be anything, Newton or meter, centimeter. Now this is a beam. Okay, let's call the beam as AB. So what we are supposed to do, we have to determine the deflection at the free end. Deflection at the free end. Okay, now how do we solve it? So we start with, let us consider any distance x from the free end. Okay, so let's consider this as a distance x from free end. So this is a x distance. Now at this particular distance, let us write down the moment. So what is the bending moment at this point? Okay, so what is the bending moment here? Can you tell me? Bending moment at any distance x? I think it's very easy, right? So P into distance, load into perpendicular distance. So bending moment will be bending moment for this will be load into perpendicular distance. That means it's simply P into x. Okay, so this is our value over here. Now let us use the strain energy formula. We have the strain energy formula as, now how this formula came? So for that you can revisit the lectures given in Ekeeda. Okay, so here strain energy is equal to 0 to L. Okay, full span we are considering, that's why we are considering 0 to L, and then the formula is m square dx by 2ei. M square dx by 2ei. Okay, so this is the formula you have to refer. Now m square you can write it as p square x square. So here p into x square by 2ei. So 0 to L, px, it will become p square x square by 2ei, again dx. Now we are going to use the integration. Now let us take out these constants. Okay, so p square by 2ei, take them out over here. Now the remaining part, 0 to L x square dx. So what we will write? X square will become x cube by 3. Okay, so let's write down p square by 2ei into x cube by 3. Okay, and it is 0 to L. So we'll get the answer as p square L cube by 6ei. Okay, so our strain energy, our answer will become as, it will be final strain energy answer. Strain energy is equal to p square L cube by 6ei. Okay, so this is our strain energy value. Now work done by the load. Okay, so this is one part of the problem. So that's what we know, the strain energy we have calculated. Now let's see what is the work done by the load. So we write down work done by the load by the load is equal to, it is given as half into P into delta. Okay, so half into P into delta. So this is work done by the external load. This is work done by the external load. Now let us compare equation number 1 and 2. Okay, so this is, let's call it as equation number 1. So this is because of the strain energy internal, okay, and that is the external. So let's compare these two equations, equate equation number 1 and 2. So we'll get, so what was the first value? It was P square L cube by 6EI is equal to half into P into delta. Okay, so P and this P will get cancelled. Okay, so delta will be, and this 2 will come this side. So we will get the answer as PLQ by 3EI. So this is the deflection. Okay, so this is the deflection. So this is our answer, and this we have done because of the, as per the, from the conservation of energy. We could equate this from the conservation of energy. So wasn't it easy, right? What is that you are expected to remember? Okay, so you have to see, you have to remember the basic formula for strain energy. Okay, so you remember this particular formula. So here, what is that for any problem? Okay, so problem may be different. So you have to find out what is moment. Okay, so once you calculate moment, simply use the integration. Okay, substitute here in this, and then use the limits, and you will arrive at the strain energy. Okay, so once you are done, so this is because of the this is the first equation of strain energy, and then because of external load we write down the formula as half into P into delta. Okay, so that is the work done by the load. So once you get these two equations, then just compare it, and then you will get the final deflection. So this was the simple example. Now let's consider one more example. So now let's consider a simply supported beam. Okay, so let's consider a beam. So this is a simply supported beam. Okay, and at this point there is a 60 kilonewton load acting. Okay, here. So that is a 60 kilonewton load. And the span here, it is EI, and this is 2EI. And this span is 4 meter. This span is 4 meter. Okay, so this is here. We have to determine the deflection under. So question says determine the deflection under 60 kilonewton load. Okay, so this is our question. Now here, with this you can see that one load is acting in the middle, and the span is 4 meter 4 meter. So you don't have to go, you can simply guess here that because load is acting in the middle, so the reactions at A and B will be, they will be same, right? So it will be Ra plus Rb equals to 60 kilonewton Okay, when you use equilibrium equation, summation of forces in y direction is equal to 0, and you can write Ra plus Rb is equal to 60 kilonewton. And here you know that Ra is equal to Rb because load is acting in the middle. So it will be a 30 kilonewton answer. Reaction will be 30 kilonewton. So now when we consider, if we consider a section at any distance x, we may consider from the left side or right side. Okay, so from any one side, if we consider section from any one end, so our moment value, because our steps are, we have to calculate moment first. Okay, because we are calculating strain energy. So in that case, if you see here, okay, we are calculating strain energy. For that we need to consider moment. So here we have considered, in previous problem we have considered any section x, but this was a cantilever beam, so we have started with the free end. But now this case, it's a simply supported beam. So for simply supported beam, for this particular case reactions are same, so we may consider section from any one side. So in that case, suppose we are considering from this side, okay, so then in that case our, if let us say this is x, okay, or say from this side, or if you consider any one side, so our moment equation will be same. This is 30 kilonewton and this is also 30 kilonewton. So any one side we can start our calculation. So here our moment equation will become any distance x will be equal to 30 into x. Okay. Now let us use the strain energy equation. So what is strain energy equation? It is 0 to L m square dx by 2EI, right? Now here substitute, there are two spans. So one span is here, other span is here. Now what we will do, we'll consider one span from the calculation from this side and this side as well. Okay, so two spans are there. So let's start with the left side. Okay, so let us write down 0 to 4 because the length is 4 meters. So 0 to 4 and the m value is 30x, right? This is the bending moment. This is the bending moment value. So what we'll write? 30x square dx divided by 2EI. Okay, so this is done. Then next, here also 0 to 4 from this side. Okay, so this way we are covering the whole beam. So now we have to be careful. Here it is single EI, okay, but here it is 2 EI. So we have to be careful while writing the EI value. Now here again 30 square divided by, here it is 2 into 2 EI. Okay, now do the calculation. So 0 to 4, 30, this is x square, so it will become x cube by 3, and this 2, 30 x square, sorry, so it will become 900. Into 900 divided by 2 into, then we will write here x cube by 3. Yeah, in that case we will use that as a limit. Okay, so this is first part. Then let's use the second part. Again here 900 by 4, 4 will come out, and again here x cube by 3, 0 to 4. Okay, so add the values of, so 900, 4 cube, this is by 3, plus 900, 4 cube by 3. Okay, so when you do the summation, we get the answer as 14,400 by EI. Okay, so this is a strain energy. So use this and get this answer. So this is the value of strain energy. Now this is the first part. So let us call it as equation number 1. Okay, let's call it as equation. So strain energy is equal to, now let's go. So this is the strain energy. Now let's go for the work done. Work done by the load. Okay. So let's write down work done by the load. It is, it is again half into P into delta. So we know P value, that is 60 kilonewton into delta. This is our equation number 2. Okay. So now equate equation number 1 and 2. So this is 14,400 divided by EI is equal to half into 60 into delta. So with this, delta is equal to, so finally we'll get the answer as 480 by EI. Okay, so the deflection is 480 by EI. So this is the answer for our beam when there is a simply supported beam. So this is the deflection when load is acting here in the middle. Now if you are if you can observe it, okay, so this both the examples for cantilever and for simply supported, okay, what we have done exactly in this case, that we could find out the deflection only where load is acting, okay, and that too only single load. So that is the limitation of this method. Okay, so that is the limitation. So there are other methods as well. Okay, so the other methods are there, like, so this is only for single load. Limitation of it is only for single load we can find out, and only under the load. Deflection can be deflection under the load. Okay, so this is the only possibility. So that's why then there are two other methods: virtual work, that is also called as unit load method, and Castiglione's method. So we go with these methods where number of loads are more. Okay, so let's see a question where using a unit load method. So let me just write down the question. Okay, so let's consider one question over here. So this is unit load method. So here our question says we have to determine the deflection and rotation. Okay, we have to determine deflection and rotation. Deflection and rotation at the free end. Okay, now the for the cantilever beam. So I'm drawing a cantilever beam here. This is A, B, C. This is 20 kilonewton. This is 20 kilonewton. This is 2I. This is I. Okay. And this span here, it is 2 meter and this is 2 meter. Okay. Now, what is that expected from us? We have to determine deflection and rotation at the free end. Okay. So, our question says we have to find out deflection and rotation at the free end. So, what we are going to do? We are going to consider a unit load over here. Okay. So, we are going to consider unit load and unit moment at this end. Okay. So, let us redraw this beam. So, here with unit load method, whatever our question demands, at that place we consider the unit rotation or unit moment. Okay, now here at this point let us consider a unit load. Here unit load and there will be a unit moment as well. So this is 1 kilonewton and this is 1 kilonewton meter. Okay, so these are the two cases because our question says deflection and rotation at the free end. Now again we have to find out what are the bending moment expressions. Okay, we need to calculate the bending moment expression. So what we have to do, we will now have, because of unit load also moment will be there, right? Because of this particular case, say case A and the condition case or condition A, condition B. Because of this particular condition there will be a moment. Okay, let us call it as small m. We are going to calculate moment for this and we are also, or say m1. Okay, and because of this unit load also, unit moment rotation also, we will be calculating moments. So let us call it as m2, and because of the external load there will be a moment m. Okay, so these three cases will be there. So we have to calculate three moments. Okay, three moments equations will be there. Now let us form a table and write down all those values. Okay, so here in this table we are going to consider the these two parts like CB and BA. Okay, two portions of the beams are there. So let us write down okay, so let's write down the member name. What are the members we are going to use? And then the member names are CB and BA. CB and BA. Now what is the origin for this? What is the start point for the calculation we are going to consider? For CB member, origin will be C. For BA member, origin will be B. Okay, so like that we are going to write. Then write down the limits. Means when you say origin, when you decide on the origin, then you will consider the distance from that point only. Like for CB member, if I am considering origin is C, then my limits will be from 0 to 2 here. Okay, so I will write 0 to 2. And when I say member BA, means my limits will start from here. So I will write 0 to 2. Okay, so let me write 0 to 2. Now let's write down the moment equation. Because of the external load, okay, we are writing capital M. Because of the external load, now when I consider any distance x over here, okay, let us consider any distance x at this point. So at this distance, our moment will be 20 into x. Okay, so this is going in a, okay, this is for this cantilever beam, it will be in a hogging shape. Okay, so bending moment will be negative. So we'll write minus 20 into x. Okay, now for the BA portion, so when you consider a distance x over here, so we will be writing, Okay, so distance x will be from this point. So we will be writing 20 into 2 plus x, 20 into 2 plus x, okay. So our equation will be minus 20 into 2 plus x, okay, because this whole 2 meter plus x, and then minus 20 into x. Or simply when you take minus outside, then our equation will be like this. Okay, so this is our equation because of the external loading. Okay, now let's consider the unit load. So for unit load also we have to write similar expressions. Now let's write for the unit load. So unit load, let's show it by small m, m1. Okay, unit load 1. So here your equation will become 1 into x, right? So let's write down minus x minus 1 into x. And similarly for this case, okay, for this case here it will be, this is 2, okay, this will be minus of x plus 2, okay. So this is total 2 and this is x, okay, x plus 2 will be there. Now because of m2, now when we consider the rotation at this point, so for the rotation our equation will become, there is it's a rotation, okay, already moment is given, so we will simply write down rotation as minus 1 and this also minus 1. So this becomes our because of the unit load, this becomes our moment equation. Now here let us also note down what are the moment of inertia I value given. So I is given for CB portion, it is I only, and for BA it is 2I. So this table, once you construct this table carefully, then remaining is just substitution part only. So then remaining calculation becomes really easy. Okay. So let's write down the equation. Okay. So what is the equation for deflection? Using unit load method, we use this formula. Okay. So you remember 0 to L m into m1 dx by EI. M into m1, okay, because we are finding out deflection. So for that we are using, this is part of the deflection, so we are multiplying these two things, okay, m into m1. And when we have to calculate rotation, okay, theta, in that time we are going to multiply m into m2. Okay, so these are the two stages we are going to do. Now here m into m1, so let's multiply it. 0 to, for first part it is 0 to 2, and m value is minus 20x into minus 20x into minus 1x, minus 20x into minus 1x divided by E into I naught, plus 0 to 2, 20 into 2 plus x plus 20x into this minus minus will become plus, okay, x plus 2. So we are multiplying these two terms. Now here EI term is different, it is 2 EI, so you have to be careful, it is 2, yeah, here it is 2 EI, okay. So that you have to substitute. So once we do the integration, now this will become 20 x cube. So let's go to next page. So our equation will become 0 to 2, 20 x square by EI, x square by EI into dx, okay, and then plus the next part 0 to 2. So here if you see 22 plus x into x plus 2, okay. So this 20 into 2 will become 40. 20 into x will become 20x, then 20x plus 20x will become 40x, okay, and then it will be multiplied with 2 plus x. So then we can write it as 40x plus 40 into x plus 2 divided by 2ei into dx. So here this will 20 into, then do the integration part, so it will become x cube by 3. So here ei we will take it out, this will become 0 to 2 plus, then this when you multiply, let's take out this 2ei part outside, then 40 into x, 40x square, right, when you multiply this and this, so it will be 40, after integration it will become x cube by 3, then 40 into x, 40 into x will become, and then 40 x into 2, so 80x, so for that will be total of 120. So 120 into x square by 2 this is 120 plus, then last part, okay, that is 80 into x by 2, and for whole bracket limits are 0 to 2. So now you do the calculation. So here it is 20 into okay 2 cube by 3, then here it will be 40 into 2 cube by 3 plus 120 into 2 square by 2 plus 80 into 2 by 2. Okay, so here once we do this calculation we will reach at 53.333. okay, do the calculation by ei plus 1 by ei 253.333. okay, so when we do the calculation, when you do the addition, your answer will be 306.67 ei. So this is the value of delta. Okay, so we could find out delta is equal to 306.67 by ei. This is our answer. So what we have done here, we have multiplied m, okay, capital M, that was because of the external load, into m1. So that gave us answer for deflection. Okay, so we got the deflection answer. Now let's calculate the rotation part. Okay, so for rotation part we have to multiply these two brackets. For rotation, what we are going to do, we are going to multiply m with m2. Okay, means minus 20x into minus 1, and this whole portion into minus 1. Okay, so rotation means theta. Okay, so rotation at the free end, rotation at C point. Okay, that is the free end only. Yes, correct. So theta C is equal to 0 to L m into m2 divided by ei. Now there are two portions, okay, two parts of the beam, that is C to B, B to A. Okay, so for C to B, our 0 to 2 limits. Okay, so it is 20 into, as just now I have shown, minus 20x into minus 1x. So 20 into x into x. So we can simply write down 20 into okay divide by ei. Then the second part 0 to 2, that is write down the complete expression. So here we when we have simplified it, so we have arrived at this expression, right? 40x plus 40. So when you simplify it, okay, we get 40x plus 40 into minus 1 we have to do. So here these are two negative expressions. So minus minus it will become plus. So into dx by 2ei. So we can rewrite this expression as 20 into x square by ei 0 to 2 dx plus 0 to 2 40 x plus 40 by 2 ei into dx. Okay, so here 20 x square by 2 will become x cube by 3. Oh sorry, here it is 1, right? So there is a slight mistake over here. So it cannot be, it is x only. So there is a mistake over here. Okay, unit load we are multiplying with the that rotation value is 1 only. So it is x only. So it will be x square by 2. Yeah. So this is 0 to 2 and the ei, let's take it out of the bracket. Then again let's take out this ei outside the bracket, and then our value remains as 40x square by 2, okay, plus 40x, that is 0 to 2. So here we get the answer as, okay, when we substitute value 40 ei plus 160 by 2 ei. So finally we get the rotation at C is equal to 120 by ei. Okay, so this is the rotation value. So here when we consider such case, okay, more than one load is there, so and what is the question asked? Okay, so it's been asked to us that deflection and rotation at the free end. So what we have done, we have considered one unit load at the free end, and then we have considered one more case, and then it is a, okay, these two cases we have to combine. Okay, so this case number 1 kilonewton load acting, and here 1 kilonewton meter rotation is there. So for this then this formation of table is important, where we are giving all the information, how we are considering the member, what are the limits. So it becomes, it's not compulsory that you have to write down the table, but when you form the table it becomes easy. Sorry. So then when we calculate deflection, so we consider the that moment part which is because of the deflection. Okay, so we multiply it with the external moment because of external load, and then because of the unit load. So that is one, it gives us deflection. And for the rotation, then we consider the capital M and the small m, that is m2, because of the rotation. Okay, so these are the two questions we have considered till now. So there are so this is with the help of unit load method. Okay, so if any doubts are there, you can ask me. And then there is one more method which is called as Castigliano's method. Okay, so Castigliano's theorem is also there. So in that case, we consider, instead of unit load, we consider a load P. Okay, in that case, so suppose so in that case I will just show how do we form the equations. Okay, So this is the third method, Castigliano's method. So in this case, if this is a beam, okay, here one end is hinged, then there is one support B, and there is one load acting over here. This is A, B, C. Okay, and this is a 3 kilonewton load acting over here. This is 6 meter, and then this is 2 meter span. Now in this case, what we are expected, it is asked to calculate vertical deflection. Okay, we have to calculate vertical deflection at the free end. And rotation at A. Okay, and this is a overhanging beam given, okay, for us, and EI is constant. So this is the data available with us. So I will just go through the procedure. Okay, how do we solve it? So what do? We have to find out what is the vertical deflection at the free end, means we have to calculate the deflection at C. Okay, so to calculate deflection at C, what we are going to do, we are going to replace this 3 kilonewton load with P. Okay, consider the 3 kilonewton, because our question is we have to find out deflection at point C. So consider this 3 kilonewton load as P. Okay, now here when we consider it as P, then we are going to calculate the reactions. So calculate reactions in terms of P. So we can write that this is RB and this is RA. So with this, let's consider moment about A is equal to 0. Okay, so we can write that if we call it as P, so P into 8 meter. Okay, so P into 8 meter is equal to RB into 6. So with this we get the RB value as 4 by 3 or 8 by 6 of P, means 4 by 3 of P. Okay, so we got the RB answer. Now once you know RB value, our summation of forces in our equilibrium equation says that RA plus RB is equal to P. So in this case our RA will be 1 minus 4 by 3, right? So it will be P by 3. And this is more than 1, right? 4 by 3. So if it is in upward direction, this P by 3 will be in downward direction. So how it will look like? So it will look like this. So if this is a beam, so this P by 3 is going down actually, and this is going up, and the total load acting is P. So this is a way how we place the load. This is P, this is 4 by 3 P, this is P by 3. Okay, so bending moment here. Now we are going to calculate the bending moment expressions. Okay, so I will write the bending moment expressions, and then I will tell how to calculate the rotation. Okay, just I will give the instructions because time is less for us now. So bending moment here. So let's see the portion. Here it is A, it is B, it is C. So let's consider the portion. So quickly draw a table. So see the member. member, and members are AB and BC. Okay, so what is the origin for AB? Let's say A. Okay, A is always good because it's from the starting part. For BC, C is good. Okay, it's starting from C. Then let's write down the limits. So limits will be 0 to 6 and here it is 0 to 2. Okay, now the capital M moment equation. So now because of P, okay, because of P, what will be the moment at AB part? Okay, what will be the moment over here? So it will be X minus P into, so when we calculate this part, so it will be P into, suppose this portion for AB member, it is starting at here, okay, or here, let's say here. So this is our X distance, 0 to 6, okay. So our equation will be minus P by 3 into X, minus P by 3 into X, okay, is going in a anti-clockwise direction. And for BC part, it will be P into X, this will be X, okay. So in that case, our answer will be minus P into X, okay. So here also it is actually a hogging shape, okay. So that is also a minus. Now here flexural rigidity is given as constant, okay. So EI is given as constant, flexural rigidity, it is constant throughout. So once we are done with this, let's substitute these equations in strain energy, okay. So strain energy equation, like we started with the class, so we have used this equation. So 0 to L, it is 0 to L m square dx by 2EI into dx, okay. So this was our equation. So now there are two parts over here. So for two members, first part is of 6 meters, so 0 to 6, so m will become, just see here, okay, m square, so square of it, and for the second part, square of it. So it will be p square x square by 9 into 1 by 2 EI dx, then plus 0 to 2 p square x square by 2 EI dx, okay, the other part of the member. So when you substitute value, okay, so when you do the calculation, it will be p square, this part will become this 9 into 2, 18 outside, then this will become x cube by 3, 0 to 6, then here it will be p square, x square will become x cube by 3, so 3 into 2, 6 EI, and then this is 0 to 2. Okay, so when you substitute all the values, finally we will get the answer as 5.333 p square by EI. So with this, our deflection at C will be, what we have to do, we have to differentiate this equation, okay. So we have to do du by dp. So du by dp, when you differentiate this, 2 into 5.333, so our answer will become 10.667 p by EI. Okay, this is our answer. Now let us substitute this P is equal to 3 kilonewton. Okay, P is equal to 3 kilonewton. Then when you substitute, our answer becomes delta C is equal to 32 by EI. Okay, so this is our answer. So this is the deflection at C point. Now let us quickly do the rotation part. So for rotation calculation, again multiply those two equations. So here for this rotation part, yes, we have to apply, because the question says determine the vertical deflection at the free end and rotation at A in the overhanging beam. Okay, rotation at A portion we have to consider. So here what we have to consider, we have to apply. So this is for rotation at A. So we have to apply dummy moment. Okay, apply dummy moment at A. So let's So this is 3 kilonewton load, and the dummy moment, see, it is at as M. There is a reaction RA over here. This is 6 meter, 2 meter, we know that. Okay, this is 3 kilonewton. Now let's consider moment about support B is equal to 0. Okay, and again calculate the RA value. Okay, so this is a totally different case when we have to calculate rotation at support A. Okay, this is A. So our equation becomes, when you consider moment about B, so what all values there? So there is, we can see RA is there. Okay, so just see the right side portion of the B. So we get the RA. So RA into 6. So this is clockwise and this is anti-clockwise. So we can write RA into 6 equals to M. So this M will be there. Oh, sorry. And there will be also a moment above from this overhang. Okay, so there will be moment. So it will be, let me just rewrite. This is the overhang portion. Okay, so RA moment about B, RA into 6 minus M, and then this is again in clockwise direction. This is for clockwise. So 3 into 2 plus 3 into 2 is equal to 0. Okay, so in this case our RA value will become M minus 6 by 6. So we can rewrite it as M by 6 minus 1. Okay, now quickly consider the construct the table. So that table will be like this. So this is AB, this is BC. So here origin, limit. So origin is A here, okay, AB, and this is C. Origin is C here. So this is 0 to 6, 0 to 2, and M is equal to, okay, this is RA, right? So consider moment about this point. This is X. Now M value, we know the RA is equal to M by 6 minus 1. So we want to see what is the moment at AB portion. So that RA into X distance will come. So M by 6 minus 1 into X. And again this moment is there, minus M. Okay. And for this particular part, when you consider moment about any distance X, moment at any distance X, so it will be minus 3 into X. So once you get the equation, then again the similar way substitute the answer. Okay, so when you substitute your answer in the equation, so you get that, so it is 0 to 6. Use this equation, M square dx by 2ei, so M by 6 minus 1 x minus M by 2ei. This is the whole square, okay, dx, plus 0 to 2 minus 3x whole square by 2ei, okay, into dx. So upon solving this, you need to spend little time on this solving. So we arrive at the equation which gives us du by dm is equal to 0 to 6 2 into m by 6 minus 1 x minus m into x by 6 minus 1 dx by 2er is equal to 0. Okay, so here what we have done for this particular equation, we have differentiated it. Okay, so we have, like here also we have done the previous case also. Once we are done here, then what we have done, we have differentiated this equation, and then we got the deflection. Similarly, here also we are differentiating this particular equation. So differentiate it. So after differentiation, we are getting this particular equation. Now we know that M is a dummy moment, right? It's a dummy moment. So we can simply substitute as 0. and then do the integration. Okay, so du by dm. So don't, before that, just don't substitute, because otherwise you will you know you have to use lot of calculation, you will use so much of energy in that. So when this becomes 0, it's only minus of x will remain here, minus x. So once this is done, then it is 1 by ei 0 to 6 minus x square by 6 plus x dx. Okay, when you simplify it, it will further give us 1 by ei minus x cube by 18. Okay, this will be x square by x cube by 3. So 6 3s are 80 plus x square by 2. It is 0 to 6 dx. Okay, so here you will get the answer as 6 by ei. Okay, so what we have to remember here, that we have to first, the note that we have to first differentiate with respect to dummy load, and then we have to substitute dummy load as a 0 and then integrate. Okay, so these are the important points, that first differentiate with respect to, first differentiate with respect to dummy load. So first we have differentiated, okay, and then substitute that dummy load is equal to 0, and then integrate. Then you integrate. So this is a 3-step procedure to get to reach to the final value. Okay, so this is our rotation. So students, hope you have understood these 3 questions what we have solved. Okay, we have actually covered 3 methods. Okay, here in this class we have studied about the strain energy procedure, we have studied the virtual work method, and we have also solved a problem using Castigliano's method. So hope this class